You are listening to The Enduring Code, building resilient software with clean architecture. Subscribe to keep up to date on our latest audiobooks. The Enduring Code, building resilient software with clean architecture. Chapter 1, The Invisible Structure, Why Architecture Matters. In the world of software development, crises seldom announce themselves with a bang. Instead, they often begin with a quiet hum, a subtle slowing down, a growing sense of unease. A project that once moved at lightning speed starts to feel sluggish. What used to be a simple fix now requires days of careful maneuvering through an intricate web of code. Adding a new feature, once celebrated, becomes an act of carefully balancing on a fragile structure, with the constant fear that any misstep will bring the whole thing crashing down. This creeping paralysis, born from unmanaged complexity, is the silent crisis of poor software architecture. Many development teams experience a similar paradox. They prioritize speed and immediate delivery. New features are launched quickly, and initial results are impressive. But as the system grows, the pace inevitably slows. Each new line of code seems to introduce more problems than it solves. Developers find themselves spending more time understanding existing systems than building new ones. This isn't a problem of individual competence, it's a structural issue. It stems from the fundamental organization of the software itself, its architecture. What is software architecture? When we talk about software architecture, we're not just referring to a fancy diagram on a whiteboard or a brief outline of technologies used. Software architecture is much more profound. It encompasses the fundamental organizational structures of a software system and the high-level decisions that define these structures. These are the choices that are difficult and expensive to change once made. Think of it like building a house. The architecture isn't merely the decorative paint color or the choice of furniture. It's the foundation, the load-bearing walls, the plumbing, and the electrical systems. These underlying structures dictate how robust the house will be, how easily it can be expanded or modified, and whether it will stand the test of time. Similarly, software architecture is the skeleton of your application, not its superficial skin. It's the framework that determines its rigidity, its flexibility, and its capacity for growth. Every piece of software has an architecture, whether it's consciously designed or not. An undesigned architecture is often a chaotic, accidental one, evolving organically through quick fixes and siloed decisions. While this can provide rapid initial progress, it almost always leads to significant long-term costs. The cost of poor architecture. The hidden costs of poor architecture are substantial and often underestimated. They manifest in various insidious ways. Rigidity. Imagine trying to move a single brick in a poorly constructed wall, only to find that it necessitates rebuilding an entire section of the house. In software, rigidity means that a seemingly isolated change in one part of the system unexpectedly demands changes in many other, seemingly unrelated parts. This makes development slow and unpredictable. Fragility. This is the unsettling experience of introducing a new feature or fixing a bug, only to discover that it causes unexpected failures in existing, previously stable parts of the system. It's like pulling on a thread and watching a sweater unravel. Fragility erodes confidence and turns every modification into a high-stakes gamble. Immobility. When components of a software system are hopelessly tangled together, they become immobile. It becomes impossible to separate and reuse them in other contexts, or even to replace a specific part without tearing down everything connected to it. This limits options for scaling, integrating with new systems, or even building new features using existing logic. Non-testability. In a poorly architected system, components are often so interconnected that they cannot be tested in isolation. This means developers must test large portions of the system at once, making tests slow, unreliable, and prone to environmental configuration issues. This significantly slows down the development cycle and increases the rate of undetected bugs creeping into production. You can't be confident in your changes if you can't test them effectively. Developer burnout. Perhaps the most significant and often overlooked cost is the human toll. Working day in and day out on a brittle, opaque, and unmanageable code base is demoralizing. Developers spend more time fighting the system than creating value. This quickly leads to frustration, inefficiency, and ultimately, developer burnout and high team turnover. The joy of creation is replaced by the drudgery of maintenance. The promise of good architecture. In stark contrast, thoughtful software design, rooted in sound architectural principles, leads to a completely different outcome. It's an upfront investment that pays dividends over the entire lifespan of the software. Good architecture acts as a force multiplier, enabling long-term maintainability. A well-structured system is easier to understand, navigate, and modify. Changes can be localized, reducing the risk of unintended side effects and making maintenance a predictable task rather than an ongoing crisis. Adaptability to new requirements. Business needs change constantly. A good architecture anticipates this by creating flexible boundaries, allowing the system to readily adapt to new features, integrate with new technologies, or pivot to new business models without requiring a full rewrite. Easy testability. When components are separated and dependencies are controlled, individual parts of the system can be thoroughly tested in isolation. This means faster tests, more reliable results, and higher confidence in the correctness of the software. Faster, more reliable feature delivery in the long run. While there might be an initial investment in design, the reduced friction for changes, the ease of testing, and the elimination of fragility mean that new features can be added with speed, confidence, and fewer bugs in the long term. This accelerates overall project velocity beyond what a rushed, unarchitected approach can ever achieve sustainably. Consider the tale of two software projects. Let's call them Lightning Launch and Enduring System. Lightning Launch was born from a startup's desperate need to capture market share quickly. The team, full of eager young developers, was urged to just get it working. Architectural considerations were minimal, seen as an impediment to speed. Features were bolted on wherever convenient, databases were accessed directly from user interface code, and business logic was sprinkled throughout the application. In its first 3 months, Lightning Launch released an impressive number of features, earning initial praise and attracting investment. But then, the quiet hum began. Adding a new payment gateway, for instance, required changes in half a dozen different places, some of which inadvertently broke existing customer notification features. Tracking down a database performance issue meant wading through thousands of lines of tightly coupled code. Fixing one bug often revealed 2 more. The initial burst of speed quickly faded, replaced by constant firefighting. Developers were spending 80% of their time on maintenance and only 20% on new features. The cost of change skyrocketed and customer complaints mounted. Eventually, the product became unmanageable, its initial promise choked by its own unarchitected complexity. It was quickly abandoned for a complete rewrite. Enduring System, on the other hand, took a different path. From the outset, the team understood the importance of a solid foundation. They invested time in defining core business rules, separating them from user interface concerns and database details. They established clear boundaries between different parts of the system and defined how these parts would communicate. Initial development felt slower. There were more discussions about interfaces and dependencies before any visual elements or database tables were created. Some stakeholders grumbled about the perceived sluggishness. However, once the core architecture was in place, the pace accelerated remarkably. When the business decided to pivot and offer a new type of product, much of the existing core logic could be reused with minimal modifications. When they decided to offer a mobile app in addition to their web application, the existing business rules could be leveraged without rewrite because they weren't tied to the web interface. Testing new features was fast and reliable because the core logic was insulated and easy to unit test. Enduring System, despite its slower start, quickly surpassed Lightning Launch in terms of feature velocity, stability, and adaptability, becoming the stable, profitable foundation for the company. This is the promise of good architecture. It protects your investment. It allows your software to evolve, to adapt, and to continue delivering value long after the initial excitement of its launch has faded. It transforms a rapidly aging liability into an enduring asset. The structure, though invisible to the end user, defines the very lifespan and success of your creation. In the chapters that follow, we will explore clean architecture, a powerful framework designed to help you build precisely such enduring systems. Chapter 2: The Roots of Resilience. Architectural Principles Revisited. Software architecture, much like any advanced craft, does not spring from a void. The principles underlying clean architecture, which we will explore in detail, are not arbitrary rules invented out of thin air. Instead, they represent the distilled wisdom of decades of collective experience in building complex software systems. They are the practical guidelines derived from learning what works and, more importantly, what doesn't. Understanding these foundational principles is crucial, as they illuminate the why behind clean architecture's structure and its enduring power. At the heart of many robust architectural styles, including clean architecture, lie a set of fundamental design principles. Among the most widely recognized and impactful are the SOLID principles, an acronym coined by Robert C. Martin, also known as Uncle Bob, to encapsulate 5 core concepts. While originally discussed in the context of object-oriented programming, their spirit applies broadly to software design at any level of granularity. The SOLID principles. A conceptual overview. It's important to approach these principles from a conceptual standpoint, focusing on their intent and how they contribute to well-designed software, rather than getting caught up in specific coding syntax. The Single Responsibility Principle, SRP. A module should have one, and only one, reason to change. Imagine a multi-tool that tries to combine a saw, a hammer, a screwdriver, and a wrench. While convenient for minor tasks, if you need to perform heavy-duty sawing, the multi-tool is cumbersome and inefficient compared to a dedicated saw. Similarly, in software, if a single component has multiple, unrelated responsibilities, it means there are multiple different reasons for that component to be modified. If your order processor component handles both calculating order totals and sending customer notifications, then a change to tax calculation rules or a change to email template formatting could both necessitate modifying that same piece of code. This violates SRP. By ensuring each component has only one reason to change, you create smaller, more focused, and more resilient building blocks. Changes become localized, and the risk of unintended side effects is drastically reduced. The Open-Closed Principle, OCP. Software entities should be open for extension, but closed for modification. This principle is about allowing your system to grow and adapt without constantly tinkering with existing working code. Think about a modern web browser. You can extend its functionality by installing new plugins or extensions without needing to modify the browser's core code. The browser is open for extension. It provides mechanisms, like APIs, for others to add features. But it's closed for modification. You don't download the source code and alter it just to add a new tab. In software design, this is often achieved through the use of abstractions, such as interfaces. You design your system so that new behaviors or variants can be added by implementing an interface or extending a base class, rather than by altering existing, proven code. This significantly improves stability and reduces the risk of introducing bugs into previously stable areas of the system. The Liskov Substitution Principle, LSP. Subtypes must be substitutable for their base types without altering the correctness of the program. This principle addresses the critical aspect of inheritance or polymorphism. If you have a general type, say vehicle, and then specific subtypes like car and truck, LSB dictates that if your system expects a vehicle, it should work flawlessly whether you provide a car or a truck, as long as they both adhere to the vehicle contract. For instance, if the vehicle contract states it can move forward and backward, then both car and truck must be able to do so predictably. If a truck subtype somehow changed direction unexpectedly or broke the expectation of a vehicle, it would violate LSB. This principle ensures that abstraction works as intended, leading to robust and predictable system behavior, especially when dealing with different implementations of an interface or base class. The Interface Segregation Principle, ISP. Clients should not be forced to depend on interfaces they do not use. Imagine a universal remote control for a home entertainment system with buttons for every conceivable device. Blu-ray players, VCRs, remember those? Smart thermostats, and even dishwashers. If you only have a TV, you're now burdened with a remote full of irrelevant buttons and functions. ISB suggests that clients, the parts of your system that interact with a component, should only see the methods relevant to their specific needs. Instead of one large, sprawling interface that encapsulates every possible operation, it's better to have several smaller, focused interfaces. This promotes thinner, more cohesive contracts, reduces coupling, and makes components easier to reuse, as clients only need to implement or use the specific functionalities they require. The dependency inversion principle, DIP. High-level modules should not depend on low-level modules. Both should depend on abstractions. Abstractions should not depend on details. Details should depend on abstractions. This is arguably the most crucial of the solid principles when it comes to understanding clean architecture. In traditional programming, higher-level logic, e.g., process and order, often directly calls lower-level details, e.g., save order to SQL database. This creates a tight coupling where the high-level logic becomes dependent on a specific low-level implementation. DIP reverses this. Instead of the high-level logic depending on the low-level detail, both depend on an abstraction, an interface. Think of a manager, high-level module, who needs a particular report-generated, low-level detail. Without DIP, the manager might directly instruct a specific junior employee to create the report exactly how that employee knows how to do it. With DIP, the manager defines what kind of report is needed through a generic report generation interface. Any employee low-level detail who can implement that report generation interface can then produce the report. The manager depends on the idea of report generation, not a specific employee. This fundamentally decouples the high-level logic from the low-level implementation details, making the system incredibly flexible and testable, which we'll see is a cornerstone of clean architecture. Abstraction and encapsulation, core concepts for managing complexity. Beyond the solid principles, two elemental concepts underpin all good software design. Abstraction. This is the act of hiding unnecessary details and presenting only the essential features of a concept or component. When you drive a car, you interact with the steering wheel, pedals, and gear shift, but you don't need to understand the intricate mechanics of the engine. The car provides an abstraction over its complex internal workings. In software, abstraction allows developers to focus on high-level behaviors without getting bogged down in low-level implementations, simplifying complex systems. Encapsulation. This is the practice of bundling data attributes and the methods, behaviors that operate on that data into a single unit and restricting direct access to some of the component's parts. It's about keeping related things together and protecting internal state from external tampering. By encapsulating behavior and data, you ensure that alterations to internal implementation details don't inadvertently impact other parts of the system, fostering modularity and maintainability. Separation of concerns, the guiding star. The philosophical umbrella under which all these principles reside is the separation of concerns. This is the fundamental idea of dividing a software system into distinct parts, each responsible for a specific functionality, with minimized interdependencies. Each concern is a distinct area of responsibility or interest. For instance, displaying data to a user is one concern, storing data in a database is another, and validating business rules is yet another. By separating these concerns, you create a system where changes to one concern, e.g., switching from a web UI to a mobile UI, are less likely to impact other concerns, e.g., the core business logic. Components are easier to understand, develop, and test in isolation. Your system becomes more adaptable as different concerns can evolve independently. Case study: a reporting system's transformation. Let's consider a simple reporting module to see how some of these principles, particularly SRP and separation of concerns, lay the groundwork for what clean architecture later formalizes. Imagine a single software component called Comprehensive Report Generator. Initially, its job is to fetch data from a database, format that data into a presentable report, e.g., a PDF, print the report to a local printer. At first glance, this might seem efficient, one class, one report, but what happens if the database structure changes, Comprehensive report generator needs modification. The report format needs to change from PDF to HTML. Comprehensive report generator needs modification. The report needs to be emailed instead of printed. Comprehensive report generator needs modification. This single class has 3 reasons to change, violating the single responsibility principle. It's rigid, fragile, and hard to test without a database and a printer. Now, let's apply separation of concerns and SRP. We introduce an iDataFetcher interface, with implementations like Database Data Fetcher and CSV File Data Fetcher. Now, Comprehensive Report Generator doesn't care where the data comes from, only that it can fetch it through this interface. We create an iReport formatter interface, with implementations like PDF formatter and HTML formatter. Comprehensive Report Generator doesn't care how the report is formatted, only that it can be done. We define an iReport printer interface, with implementations like physical printer and email sender. Comprehensive Report Generator doesn't care how the report is delivered, only that it can be output. Now, Comprehensive Report Generator is much leaner. Its single responsibility becomes orchestrating the process of report generation, fetching data, formatting it, and printing it. It doesn't perform these lower-level tasks itself. It relies on distinct, specialized components that implement the interfaces it needs. If the database changes, only Database Data Fetcher needs modification. If the format changes, only the iReport formatter implementation needs modification. This transformation illustrates not just SRP, but also the powerful influence of the dependency inversion principle. The Comprehensive Report Generator, a high-level concept defining the process, no longer depends on concrete, low-level details, a specific database, a specific format, a specific printer. Instead, it depends on abstractions, the iDataFetcher, iReport formatter, and iReport printer interfaces. The actual, concrete implementations of data fetching, formatting, and printing then depend on these very same abstractions by implementing them. This creates a flexible, decoupled system. Precisely the kind of system that clean architecture aims to build, protecting its core from volatile external details. These principles form the intellectual bedrock upon which clean architecture stands. They guide us towards designing systems that are not just functional today, but also resilient, adaptable, and maintainable for years to come. In the next chapter, we will see how clean architecture formalizes these ideas into a clear, understandable structure. Chapter 3. The core idea: what exactly is clean architecture? If the previous chapter laid the philosophical groundwork, this chapter introduces the blueprint itself. Clean architecture, a concept popularized by Robert C. Martin Uncle Bob, is not a new invention in the grand scheme of software design. Rather, it's a distillation and unification of several established architectural patterns, like hexagonal architecture, ports and adapters, onion architecture, and boundary control entity, presenting them in a cohesive and highly practical manner. At its heart lies a single, powerful, and utterly non-negotiable rule: the dependency rule. The dependency rule, the unyielding law. This is the cornerstone, the central axiom of clean architecture. It states, dependencies must always point inwards. What does this mean? It means that inner circles, layers, of your architecture should never know anything about outer circles. Code in an inner circle must not make a reference to code in an outer circle. This includes calling functions, variables, or even declaring classes defined in an outer circle. Why is this so critical? Because outer circles represent mechanisms or details, things that are prone to change. Databases can be swapped, user interfaces can be revamped, web frameworks can come and go. The inner circles, however, represent the policies or business rules, the core value and logic of your application that should remain stable over time. By ensuring that dependencies flow only inwards, you protect your valuable core business logic from being affected by changes in these ever-evolving external details. If an inner circle were to depend on an outer circle, then a change in the outer circle would force a change in the inner circle. This reversal of dependency would completely undermine the objective of protecting the core. Analogies for the dependency rule. To truly grasp this concept, let's explore a few analogies. The onion analogy: imagine an onion with multiple concentric layers. At the very center is the core, the most valuable part. As you peel away layers, you encounter more superficial elements. The dependency rule dictates that each layer can only see or interact with the layers immediately inside it, and certainly never with the layers outside itself. The core doesn't know about the skin, and the first inner layer doesn't know about the second outer layer. This layered structure keeps the valuable core protected from external influences, fences, and boundaries. Envision a highly valuable, secret recipe kept in a secure vault, your core business logic. Around this vault, there are several layers of fences, checkpoints, and security systems. Each layer of security protects the one inside it. The vault doesn't know about the outermost perimeter fence. It only knows about its immediate protective layer. The outer perimeter and checkpoints are designed to filter and authorize entry to the precious inner contents. This strict boundary enforcement allows the outer security to change, e.g., new surveillance technology, without requiring modifications to the vault itself. Hexagonal/ports and adapters. Clean architecture draws heavily from hexagonal architecture, often called ports and adapters. Imagine your application's core business logic as a hexagon. This hexagon has several ports, clearly defined interfaces or entry points through which it communicates with the outside world. To interact with these ports, you attach adapters. An adapter could be a web interface adapter, a database adapter, a message queue adapter, or a test harness adapter. The crucial point is that the hexagon, your core, doesn't know about the specific technologies used by the adapters. It only knows about the abstract ports. The adapters implement these ports, thus fulfilling the dependency inversion principle we discussed earlier. The core dictates what it needs, the port, and the outside world provides the implementation, the adapter. The circles of control, the famous diagram. The most iconic representation of clean architecture is its concentric circles diagram. While the exact naming conventions and number of layers can vary slightly depending on the specific implementation, the fundamental principle remains the same. Let's describe the typical 4 layers, moving from the innermost to the outermost. Entities, innermost circle. What they are? These are the enterprise-wide business rules. They encapsulate the critical business policies and data structures that are foundational to your system and could theoretically be shared across many applications within an enterprise. They represent the purest form of your domain model. Independence. Entities should be completely independent of any frameworks, databases, or user interfaces. They should have no knowledge of how they are saved, displayed, or interacted with externally. Their code changes only when the fundamental business rules they embody change. Use cases, interactors. What they are. This layer contains the application-specific business rules. Use cases encapsulate and orchestrate the flow of data to and from entities to achieve a specific application goal. They define the inputs, outputs, and the specific sequence of operations required to perform a task, e.g., create an order, register a new user. Role. Use cases direct the entities and interact with them to fulfill the application's functionality. They depend on entities. Interface adapters. What they are. This layer acts as the conversion interface between the inner and outer circles. Data coming from the outermost layers, like a web request, is converted into a format suitable for the use cases and entities. Conversely, data produced by the use cases is converted into a format suitable for the outermost layers, like a JSON response or a database record. Examples: this layer contains web controllers, which adapt HTTP requests to use case inputs, presenters, which format use case outputs for the UI, and gateways repositories, which provide abstract interfaces for interacting with databases or external services. Importantly, the inner use cases define interfaces that these adapters implement, adhering to DIP. Frameworks and drivers, outermost circle. What they are. This is the outermost layer where all the details live. It contains the databases, web frameworks, user interface components, third-party libraries, and external services. These are the tools and technologies you use to make your application concrete and runnable. Dependence. This is the only layer that can directly depend on everything inside it. However, because of the dependency rule, nothing inside this layer can depend on it. The lines between the circles are the architectural boundaries. Data crosses these boundaries in specific ways, almost always in the form of simple data structures, e.g., data transfer objects or DTOs, to prevent any specific layer's models from leaking into another. The promise of independence. Adhering to the dependency rule across these layers grants your system incredible independence. Framework independence. You can joyfully swap out your web framework, e.g., from an older version of Spring to a newer one, or from Express.js to Fastify, without rewriting your core business logic. The internal layers simply don't know or care what framework is being used to deliver the application. UI independence. Whether your application is accessed via a web browser, a mobile app, a desktop application, or even a command line interface, your core business logic remains oblivious. You could theoretically write entirely new UIs without touching the use cases or entities. Database independence. This is a profound benefit. Your business rules don't know if data is stored in a relational database, a NoSQL store, or even a plain file. As long as the database adapter fulfills the interface contract defined by the use cases, you can switch databases with localized effort. External agency independence. Whether you're interacting with a microservice, a third-party API, or an on-premise system, your core logic remains insulated. These external systems are simply treated as details that your adapters handle. Why independence matters. This radical decoupling isn't just an academic exercise. It has immense practical value. Ultimate flexibility. Your system can adapt to almost any change in technology or business requirement without major rewrites. This prolongs the life of your software. Higher testability. As highlighted in Chapter 1, the core business logic can be tested in complete isolation, without the need for complex setups involving databases, web servers, or front-end frameworks. This makes testing fast, reliable, and comprehensive. Longevity of the core. Your most valuable asset, your unique business rules remain stable and pristine, protected from the volatile world of changing technologies. This preserves your intellectual property and reduces technical debt over time. Think of building a high-quality, sturdy house that is designed to last for generations. The core structure, the foundation, the load-bearing walls, the roof, is built using timeless engineering principles. These elements are designed to be incredibly robust and long-lasting, independent of fickle trends. The easily changeable aspects, like the interior decor, paint, furniture, wallpaper, or even the specific utilities, electrical wiring, plumbing fixtures, can be swapped out and updated as tastes change or as technology improves. The key is that changing the curtains or a light fixture doesn't require tearing down a load-bearing wall. Clean architecture provides you with the principles and framework to build precisely this kind of resilient software system. One where your invaluable business logic remains stable and adaptable, irrespective of the ever-changing tides of technology. Having established this core idea, we will now delve deeper into each of these layers, starting with the very heart of the system, the entities and use cases. Chapter 4, The Inner Sanctum, Entities and Use Cases. Having grasped the foundational concepts and the overarching structure of clean architecture, it's time to delve into the very heart of your application, the innermost layers. This is the inner sanctum, the most protected part of your system where the core value and specific application logic reside, blissfully unaware of database queries, web requests, or user interface nuances. These two innermost layers, entities and use cases, represent the true intellectual property of your software. Entities, the business rules that endure. At the very center of the clean architecture concentric circles diagram lies the entities layer. These are often referred to as enterprise business rules. What are they? Entities encapsulate the absolute highest level, most critical business policies and data structures. They are the bedrock of your domain, the fundamental truths of your business that would remain stable even if the entire application around them were to change drastically, or if your company decided to use its core logic in a completely different kind of system. They contain both data and the methods, behaviors that operate on that data according to the business rules. Independent nature. A defining characteristic of entities is their complete independence. They should have absolutely no knowledge of databases, web frameworks, user interfaces, or any other external details. An entity's code should change only when the fundamental, core business rules it represents change. If you have an account entity, its rules for crediting, debiting, or checking for overdrafts should be pure, unadulterated business logic, impervious to whether the account data is stored in SQL Server, MongoDB, or a ledger on Jupyter. Examples: a customer entity. This might contain a customer's name, address, loyalty points balance, and methods to add loyalty points or update address. The rules dictating how loyalty points are calculated or what constitutes a valid address are embedded within the customer entity itself. It doesn't care if a web form captured the address or if it came from an external API. An order entity. This could hold items, quantities, pricing information, and methods like calculate total, add item, or apply discount. The logic for calculating the total price, ensuring minimum order quantities, or validating discount codes would reside here. It doesn't know about payment gateways or shipping providers. An appointment entity. This might contain a date, time, and associate it with a patient and a doctor. It could have business methods like reschedule, new time, that contain rules for valid rescheduling times, perhaps checking for conflicts, but it won't be concerned with how that appointment is displayed in a calendar application. The purity of the entity's layer is paramount. It's about creating a timeless, universal representation of your business domain, one that is truly independent of any particular application, technology, or deployment context. Use cases, interactors, orchestrating business-specific logic. Just outside the entity's layer, but still very much within the protected core, lies the use cases layer. These are also often called application business rules or interactors. What are they? Use cases represent the specific, application-driven business rules. They embody the use cases, or verbs of your system, the concrete actions a user or an external system can perform to achieve a specific goal. They are responsible for orchestrating the flow of data to and from the entities and guiding them to fulfill the application's objectives. Role. A use case takes input data, applies business logic, manipulates entities, and produces output data. They define the inputs required, the business logic to execute, and the outputs to generate. Crucially, a use case doesn't know about the UI or the database. Instead, it interacts with abstractions, interfaces, defined within its own layer, or the interface adapter's layer for any communication with the outside world. Interaction with entities. Use cases are the drivers of entities. They call methods on entities and pass data to them, guiding the entities through their various states based on the application's specific needs. However, the dependencies rule applies. Entities do not know about the use cases that operate on them. Entities remain pure and oblivious to their application-specific orchestrators. Examples: create order use case. This use case would take inputs like customer ID, list of product IDs, quantities. It would then retrieve customer and product entities. Create or retrieve an order entity. Call order add item for each product. Call order.calculate total. Persist the order entity by calling an abstract order repository interface. Perhaps also call an abstract payment gateway interface to process payment. Finally, it would return a result indicating success or failure. Register user use case. This use case might take a username, email, and password. Its steps could involve validating that the username is unique and the password meets complexity requirements, hashing the password for security, creating a user entity, saving the user entity using an abstract user repository interface, sending a welcome email using an abstract email service interface. The purity of the core, the separation of entities and use cases, and their insulation from external concerns, is what gives your application its long-term stability and resilience. They represent the true, lasting value of your software. Think of it this way: the entities define what your business fundamentally is and what rules it must follow. The use cases define how your application specifically interacts with that business or what processes it performs. If you need to change how users interact with your system, e.g., from a web form to a command line interface, you change the interface adapter's layer, but the register user use case remains unchanged. If you need to switch databases, you change the database adapter, but the create_order use case and the order entity remain untouched. This clean isolation allows you to evolve your application's external details without constantly having to re-engineer your core business processes. Because these layers are so pure and have no external dependencies, they are incredibly easy to test. You can write unit tests for your customer entities, add loyalty points. Method without needing a database connection or a running web server. You can test your register user use case by providing it with mock versions of the user repository and email service, which are abstractions defined at the use case or interface adapters layer, ensuring that all its business logic for user registration is correct and independent of the actual persistence mechanism or email provider. This purity leads directly to high testability, which greatly improves the reliability of your system. In essence, the entities and use cases form the strategic central brain of your application. They encapsulate the unique knowledge and processes that define your business, protecting them from the noise and volatility of the outside world, ready to serve as the stable foundation for decades to come. In the next chapter, we will examine how this brain actually communicates with that volatile outside world through the crucial layer of interface adapters. Chapter 5: Gateway to the World. Interfaces and adapters. If the entities and use cases, as discussed in the previous chapter, constitute the brain and the core operational logic of your application, then the interface adapters layer serves as its crucial nervous system and sensory organs. This layer is the critical bridge that allows the highly insulated core to interact with the outside world, user interfaces, databases, external services, without actually knowing anything about the messy implementation details of those external components. It's the gatekeeper, ensuring that communication across the architectural boundaries adheres strictly to the dependency rule. The role of interfaces, ports, defining contracts. In clean architecture, an interface is more than just a programming construct. It's a conceptual port or a clearly defined contract that an inner layer needs to interact with an outer layer. These ports specify what operations are required or provided, but absolutely not how those operations are performed. Input ports or driving ports. These are interfaces defined by the use cases layer that external actors or drivers, like a user interface or an API client, can use to initiate actions within the application. Think of it as a set of defined entry points to your application's use cases. Example: an invaluable use case interface might be defined within the use cases layer. It declares a method like execute new order request. This interface tells anything on the outside. If you want to create a new order, you must provide me with this new order request data, and I promise to take care of it through this execute method. Output ports or driven ports. These are interfaces defined by the use cases layer that the use cases themselves use to request services from external systems, like databases, external APIs, or notification services. The use cases need certain external capabilities, and they define an interface that describes those needs. Example: an iProduct repository interface in the use cases or interface adapters layer might declare methods like find by ID, product ID, or save product. The create_order use case would then call methods on an instance of iProduct repository when it needs product information or needs to save an order, completely oblivious to whether that repository will talk to a SQL database, a NoSQL store, or even an in-memory test database. Similarly, an iEmail service interface might declare send welcome email address, username. These interfaces are vital because they define the clean boundaries that uphold the dependency rule. The inner layers, use cases, define these interfaces, the ports, and they depend on these abstractions. The role of adapters, implementing interfaces. If interfaces are the ports or the plugs, then adapters are the concrete implementations, the plugs themselves that allow actual communication. Adapters know about the outside world specifics and translate them into a format that the inner layers understand, and vice versa. Primary adapters, driving adapters. These adapters sit closest to the frameworks and drivers layer and are responsible for taking input from external sources, like an HTTP request from a web browser, a command from a CLI, or an event from a message queue, and adapting it into a form that the use cases can consume. They drive the application's core logic. Examples: a web controller, e.g., in a Spring MVC or ASP.NET controller. This component receives an HTTP request, like a post to /API/orders, extracts the relevant data from the request body, validates presentation-specific concerns, e.g., ensuring a field is not empty, and then converts this data into the new order request DTO that iNewOrder use case expects. It then calls the execute method on the iNewOrder use case. A CLI parser takes command line arguments and adapts them into a format suitable for a use case. A mobile presenter view model translates user interactions from the mobile UI into calls to specific use cases. Secondary adapters, driven adapters. These are adapters that implement the output port interfaces, like iProduct repository or iEmail service, defined by the use cases. They are responsible for taking requests from the use cases and translating them into calls to specific external resources, databases, third-party APIs, file systems. They are driven by the application's core logic. Examples: a SQL product repository implements iProduct repository. This adapter knows how to write SQL queries or use an object relational mapper, ORM, to retrieve and save product data to a relational database. When a use case calls product repository save, product, this adapter handles the database-specific communication. An SMTP email service implements iEmail service. This adapter knows how to connect to an SMTP server and send an email using the SMTP protocol. A Stripe payment gateway implements iPayment gateway. This adapter knows how to interact with the Stripe API to process a payment. Dependency inversion in action. This design perfectly illustrates the dependency inversion principle, DIP, at work, which is absolutely fundamental to clean architecture. The inner layers, use cases, and entities contain the high-level business logic. They define the interfaces, the output ports for the services they need. The outer layers, interface adapters and frameworks and drivers, contain the low-level implementation details. They implement those interfaces. Therefore, the use cases, high-level policy, depend on an abstraction, e.g., iProduct repository. The SQL product repository, low-level detail, also depends on that same abstraction by implementing iProduct repository. This cleverly reverses the typical flow of control and dependency. Instead of the use case directly calling a concrete database class, the use case calls an abstract interface, and the concrete database class implements that interface. This allows the use case to remain completely decoupled from the specific database technology being used. Analogy: the universal power adapter. Think about a universal power adapter for your laptop. Your laptop, the core business logic, needs power. It doesn't care if the power comes from a wall socket in Europe, the US, or a car's cigarette lighter. It only expects a specific type of electrical input, its port or input interface. The wall socket, the external power source in the frameworks and drivers layer, provides power in a specific format for that region. The universal power adapter, the adapter, is the crucial piece. It takes the power input from the wall socket, or car, or airplane, understands its specific voltage and plug type, and converts it into the exact format your laptop expects. Your laptop never knows about the wall socket's specific design. It only interacts with the adapter's output. The adapter, in turn, knows how to talk to both the wall socket, the external detail, and the laptop, the abstraction it fulfills. This interaction ensures your laptop, the core, remains operational globally, untouched by the variable nature of power sources around the world. Similarly, interface adapters allow your application's core logic to operate consistently, regardless of the constantly changing technologies of its surrounding environment. The interface adapters layer is where the rubber meets the road, where the abstract world of business rules finally connects with the concrete world of physical systems. It is through these meticulously designed interfaces and their corresponding adapters that your protected core gains its gateway to the outside world, setting the stage for the outermost layer. Frameworks and drivers. Chapter 6, The Outer Shell, Frameworks and Drivers. We've journeyed inward through the concentric circles of clean architecture. from the abstract purity of entities and the orchestrating intelligence of use cases, across the translating bridge of interface adapters. Now we arrive at the outermost layer, often referred to as frameworks and drivers, or simply web, DB, UI, external interfaces, and so on. This is where the concrete details of our system reside. What belongs here? This layer is the noisy, vibrant marketplace of technology. It's where you find web frameworks. These are the tools that handle HTTP requests, routing, session management, and the overall web application structure. Examples include Spring Boot, ASP.NET Core, Express.js, Django, Ruby on Rails, or Laravel. Their primary job is to receive external requests and pass them to the appropriate interface adapters, and then to take responses from the adapters and render them back to the client. Database frameworks/ORMs. These manage your application's interaction with persistence mechanisms. This includes object relational mappers, ORMs, like Entity Framework, Hibernate, SQLize, or SQL Alchemy, or direct database drivers for specific databases like PostgreSQL, MySQL, MongoDB, or Cassandra. These are responsible for translating commands from your database adapters into calls your database understands, e.g., SQL queries. User interface, UI, frameworks. This encompasses everything that draws pixels on a screen and captures user input. This might be a web frontend built with React, Angular, or Vue.js, a mobile application using SwiftUI or Android Jetpack Compose, or a desktop application using WPF or Swing. The UI layer takes structured data from the presenters, part of the interface adapters layer, and renders it for the user, and conversely, takes user input and passes it to the appropriate primary adapter. External APIs and services. Any integration with third-party payment gateways, like Stripe or PayPal, messaging services, like Twilio or SendGrid, cloud services, like AWS S3 or Azure Blob Storage, or other microservices falls into this category. These are the systems that your application uses to interact with the wider digital ecosystem. Configuration files, application settings, environment variables, connection strings, and other configuration data that vary by deployment environment. Logging and monitoring tools, the infrastructure for tracking application events, performance metrics, and debugging information. Essentially, anything that could be considered an implementation detail. A specific technology choice that is largely interchangeable without affecting the core logic resides in this outermost layer. The dependency rule revisited. This concept is so crucial it bears repeating. This outermost layer depends on everything inside it. It relies on the interface adapters, use cases, and entities. However, and this is the critical distinction, none of the inner layers depend on nor are aware of this outer layer. What does this mean in practical terms? Your web controller, in the frameworks and drivers layer, will know about and call methods on your invaluable use case, in the use cases layer, via its concrete implementation in the interface adapters layer. Your database context, or ORM, in the frameworks and drivers layer, will know about and interact with your SQL product repository, in the interface adapters layer. However, your invaluable use case knows nothing about HTTP requests or a specific web framework. Your iProduct repository definition knows nothing about SQL or the particular ORM you're using. This strict adherence to the dependency rule is what gives clean architecture its power. The freedom of choice. The true liberation offered by this architectural style comes from the freedom of choice it bestows upon your core application. Because your inner layers are completely decoupled from these external technologies, you can switch your database technology. Imagine your application starts with a relational database like PostgreSQL. Later, you realize a NoSQL database like MongoDB would be a better fit for a certain data set. With clean architecture, you only need to write a new Mongo product repository that implements the existing iProduct repository interface. Your use cases and entities remain completely unchanged. The effort is localized to this one adapter. You can change your web framework. If your initial choice of web framework becomes outdated or a more efficient one emerges, you can replace the parts of your frameworks and drivers layer and corresponding primary adapters, while your core business logic continues to function seamlessly. You can support multiple UIs. Your use cases and entities don't care if the user is interacting via a web browser, a mobile app, or a smart device. You can develop completely separate UI frontends, each utilizing its own framework driver and its own primary adapters, all talking to the same, stable core logic. This promotes significant code reuse of your most valuable assets. You can integrate with new providers. Swapping from one email service provider to another, or from one payment gateway to a different one, simply involves implementing a new adapter while your iEmail service or iPayment gateway interface, and the use cases that depend on it remain unaffected. Practical example, the journey of a web request. Let's illustrate the journey of a user request through the layers, focusing on how the outermost layer orchestrates the flow without affecting the core. User interaction, UI, outer layer. A user navigates to your -app.com/signup and fills out a form. They click Register. Web server/framework, frameworks and drivers, outer layer. The HTTP request hits your web server, e.g., Nginx Apache, which passes it to your web framework, e.g., Node.js with Express. The web framework's routing mechanism directs this request to a specific auth controller. Authentication controller, primary adapter interface adapter layer. The auth controller, a component in your interface adapters layer, receives the HTTP request. It parses the request body to extract the username, email, and password. It might perform basic input validation, like checking if fields are empty. Crucially, it then creates a simple data structure, a register user request DTO, containing just the raw data cleanly extracted from the HTTP context. Calling the use case, primary adapter to use case. The auth controller, the primary adapter, then calls the execute method on its injected iRegister user use case, defined in the use cases layer. Register user use case execute, register user request. Use case execution, use cases inner layer. The register user use case then performs all its core business logic. Checks if the username is already taken by calling user repository find by username. The user repository is an instance of iUser repository, an output port abstract interface defined in the interface adapters layer. Validates password strength, creates a user entity, persists the user by calling user repository save user, sends a welcome email by calling email service send welcome user email. The email service is an instance of iEmail service, another output port interface. Constructs a register user response DTO, e.g., containing user ID and success status. Persistence adapter, secondary adapter frameworks and drivers layer. The SQL user repository, which implements iUser repository and resides in your frameworks and drivers section, receives the save user call. It takes the user entity data, translates it into database-specific constructs, e.g., an ORM entity or SQL insert statement, and interacts with the database. The database itself is a separate process. Email service adapter, secondary adapter, frameworks and drivers layer. Similarly, the SMTP email service, implementing iEmail service, receives the send welcome call. It translates this into an SMTP protocol message and sends it to an external email server. Returning results, use case to primary adapter. Once the use case is done, it returns the register user response DTO to the auth controller, presenting the result, primary adapter to UI outer layer. The auth controller receives the response. It then translates this response into an HTTP status code, e.g., 201 created or 400 bad request, and a JSON or HTML response body, and sends it back to the user via the web framework. Throughout this entire process, the core register user use case and user entity know nothing about HTTP, Express, SQL, or SMTP. They are clean, testable, and reusable business logic, protected by the layers around them. The frameworks and drivers layer is indispensable for any real-world application, as it's what makes your software runnable and interactive. However, in clean architecture, it is consciously relegated to the status of a detail. This deliberate design choice protects the precious, stable core of your application from the inherent volatility and rapid evolution of the surrounding technological landscape, ensuring that your software can adapt and thrive for years to come. In the next chapter, we'll solidify our understanding of how data and control truly flow across these vital boundaries. Chapter 7: Navigating the Layers, Data Flow and Control Flow. Understanding the static structure of clean architecture, the concentric circles and their responsibilities, is one thing. Comprehending how dynamic processes unfold within this structure, how information moves, and how execution paths navigate these layers is another. This chapter clarifies the crucial distinction between data flow and control flow, emphasizing how both must adhere to the dependency rule without sacrificing application functionality. The direction of data flow. When an application is in use, information constantly moves across the architectural boundaries. This movement is cyclical, forming a request-response pattern. Requests inwards. When an external actor, like a user interacting with a UI or an external system making an API call, initiates an action, data begins its journey from the outermost layers, frameworks and drivers, interface adapters, towards the innermost layers, use cases, entities. The raw input from the outside world, e.g., HTTP request body, form data, command line arguments, is progressively refined and transformed. Each layer converts the data into a format suitable for the next inner layer, discarding unnecessary outer layer details. For example, a web controller, outer layer, parses an HTTP request. It then passes relevant data into a HTTP request DTO, interface adapter layer. This DTO is then mapped to a use case specific input DTO, interface adapter layer. This use case specific input DTO is finally consumed by the use case. Responses outwards. After the inner layers, use cases and entities, process the request and execute the core business logic, the results or feedback begin their journey outwards. The use case generates a use case specific output DTO containing the necessary data for the response. This DTO is then passed to the interface adapters, which convert it into a format suitable for the outer layer. Finally, the outermost layer presents this data to the user or external system, e.g., as a JSON response, a rendered web page, or a mobile UI update. Crucially, these data transfers typically involve data transfer objects, DTOs. Data transfer objects, DTOs, the currency of communication. DTOs are simple, plain data structures used solely for transferring data across architectural boundaries. They are collections of fields, data, without significant behavior methods. Why DTOs? The use of DTOs is critical for preventing leaky abstractions. A leaky abstraction occurs when the underlying implementation details of one layer become exposed to, and sometimes even dependent upon, higher layers. For instance, if a use case directly exposed its internal entity objects to the UI layer, then the UI might accidentally gain knowledge about the entity's internal structure, or even try to modify it directly, bypassing the use case's defined operations. This creates tight coupling and undermines the architectural separation. Purpose: decoupling. DTOs act as independent communication contracts between layers. They are separate from the internal entity models, the database models, or the specific UI form models. This ensures that changes to an entity's internal representation, e.g., adding a new private field, don't force changes in the UI or database layer as long as the DTO remains stable. Data filtration. DTOs allow you to carefully control exactly which data is exposed to which layer. For example, a user entity might contain sensitive fields like a hashed password. A user output DTO might expose only the username and email, ensuring sensitive data doesn't accidentally reach the UI. Adaptation. DTOs are specifically structured to fit the needs of the receiving layer. A login request DTO will contain username and password fields, while a user profile response DTO will contain different fields relevant to displaying a user profile. Mapping. The interface adapters layer is typically responsible for the mapping between different DTOs and your internal entities. It takes raw input data, e.g., from an HTTP request, maps it to an input DTO, what the use case expects, converts entity data into output DTOs, what the UI expects or what an external service needs. Control flow versus dependency flow. This is often where confusion arises in clean architecture. While the dependency flow must always point inwards, meaning inner layers never have compile time or source code dependencies on outer layers, control flow can, and often does, cross layers in both directions. Dependency flow, source code dependencies. This refers to how modules and classes know about each other at a compilation or source code level. If module A has a source code dependency on module B, it means module A imports, references, or directly uses code defined in module B. The dependency rule dictates that this kind of dependency must always flow inwards. Frameworks and drivers depends on interface adapters. Interface adapters depends on use cases. Use cases depends on entities. Crucially, entities depend on nothing. There is no dependency from entities to use cases, or use cases to interface adapters, or interface adapters to frameworks and drivers. This is achieved primarily through the dependency inversion principle, DIP, as discussed in Chapter 2 and 5. Inner layers define abstract interfaces, output ports, that outer layers implement, adapters. The inner layer depends on the abstract interface, and the outer layer implements that interface. So, both depend on the same abstraction, but the source code dependency direction is maintained inwards because the outer layer imports the interface defined in the inner layer, but not vice versa. Control flow, execution flow. This refers to the sequence of method calls or execution paths when your application is running. Control flow can move across layers in any direction necessary to fulfill a request. Let's trace a typical control flow for creating an order. User clicks a button in the UI outer layer. The web controller, primary adapter and interface adapters layer, receives the request. The web controller calls createOrder on the createOrder use cases layer. Control flow, inwards. The createOrder use case validates some input. The createOrder use case calls product repository findById on an abstract interface, output port in interface adapters layer to fetch product details. Control flow, implicitly outwards to the concrete adapter. The use case calls the interface, and the framework ensures the concrete adapter is provided. The concrete SQL product repository, secondary adapter in frameworks and drivers layer, executes a database query to get the product details. Control flow, outwards to the database. The database returns the data to SQL product repository. SQL product repository returns the data to the createOrder use case. Control flow, inwards. The createOrder use case creates an order entity. 10. The createOrder use case calls order repository save, abstract interface. Control flow, implicitly outwards to the concrete adapter. 11. The concrete SQL order repository, frameworks and drivers layer, saves the order entity to the database. Control flow, outwards to the database. 12. SQL order repository returns confirmation to createOrder use case. Control flow, inwards. 13. createOrder use case returns success message as a DTO to the web controller. Control flow, outwards. 14. The web controller prepares the HTTP response and sends it to the UI. Control flow, outwards. This constant back and forth of control flow is perfectly normal and necessary. The key is that the source code for the inner layers remains oblivious to the concrete implementations in the outer layers. It's this one-way source code dependency that provides the architectural stability. The strictness of boundaries. The seemingly pedantic distinction between dependency flow and control flow is fundamental to clean architecture's power. Any shortcut, such as a use case directly importing a database-specific class, parsing an HTTP request, or knowing about a specific UI component, would be a violation of the dependency rule. Such violations create leaky boundaries, which lead to reduced testability. If your use case knows about a database, how can you unit test it without a database always being present? Increased coupling. Your core business logic becomes tied to external details, making changes harder and cascading effects more likely. Compromised independence. You lose the ability to easily swap out frameworks or databases without affecting your core. Enforcing these boundaries is a discipline, but it is the discipline that directly translates into the long-term maintainability, flexibility, and testability of your software system. Analogy: passport control at the airport. Imagine you are arriving at an airport and going through passport control. You, the passenger, you carry data, your passport, visa, maybe a customs declaration form. You want to enter the country. The passport control desk, boundary, this is the strict interaction point. You don't walk directly into the country. You pass through this well-defined interface. The passport control officer, use case. This is the high-level policy. The officer needs specific information from your passport, your name, nationality, photo, to make a decision, allow entry or detain. The officer doesn't care if your passport was issued in a particular country's consulate in a specific city or by a specialized printing company. They only care that it meets the required format and provides the necessary data. The immigration database, outer layer/external system. The officer might need to verify your details against a large, external database. Control flow, officer's action. The officer use case requests a check from the database system, e.g., is this person on a watch list? This is a request that goes outwards to the database. Control flow, database response. The database system performs its task and returns a response, no, they are clear, or yes, they are on a watch list. This response comes inwards to the officer. Dependency flow. The officer's training manual, the code of the officer, details what information is needed from the passport and what inquiries to make to the database system, e.g., query the watchlist system. It does not contain details about specific database vendors, table structures, or the exact query language used by the database system. The officer's knowledge depends on the abstract needs for the job, not on the specific technology of the database. The database system itself, as a physical entity, depends on the officer's request format to know what to do. This entire process ensures that the core duty, the policy of allowing entry, remains robust and is independent of the underlying technology or bureaucracy of the verification systems. It's the same strict separation that clean architecture fosters, ensuring your business logic remains clear, focused, and adaptable. Now that we understand how information traverses the layers, we can walk through a concrete example of a use case in action. Chapter 8, Building a Use Case, a conceptual walkthrough. Up to this point, we've dissected clean architecture conceptually, explaining its philosophy, debunking its myths, and outlining its layers. Now, it's time to bring it all together by tracing a common scenario through every layer. We won't be diving into specific code. Instead, we'll use clear, narrative descriptions to illustrate how each component plays its part, demonstrating the dynamic interplay of data and control flow, and ultimately, how the dependency rule keeps the core pristine. Scenario: user registration and welcome email. Our chosen scenario is a classic. A user signs up for a new service. This involves gathering user details, username, email, password, validating these details against business rules, persisting the new user to a database, sending a welcome email. Let's walk through this process step by step, starting from the user's interaction and moving through the concentric circles. Step 1, user interface interaction, outermost layer, frameworks and drivers. Imagine a user visiting your website or opening your mobile app. They navigate to a sign-up page and fill out a form. Fields for username, email address, password, and a register button. This form is rendered by a specific UI framework, e.g., React, Angular, SwiftUI. When the user clicks Register, the UI framework captures this event and makes a call to your backend application, typically an HTTP post request to an endpoint like /API/register. At this point, the data is raw, coming directly from an external source, the user's browser or device. It contains technical details like HTTP headers, cookies, and the specific format of the form submission, e.g., JSON or URL encoded. Step 2, receiving the request in the backend, outermost layer. Frameworks and drivers/interface adapters. The HTTP post request arrives at your backend server infrastructure. Web server framework. Your web server, e.g., Apache, Nginx, passes the request to your chosen web framework, e.g., Spring Boot, ASP.NET Core, Express.js. The web framework's routing mechanism directs this incoming HTTP request to a specific web controller within your application. Web controller, primary adapter, interface adapter layer. This component is the primary entry point into your application for HTTP requests. Its main job is to receive, accept the incoming raw HTTP request, parse, extract the specific data, username, email, password from the request body. Basic validation, perform initial, presentation-specific validation, e.g., is the email string a valid format? Are all required fields present? This is about ensuring the input is structurally sound, not necessarily about business rules. Map to input DTO. Crucially, it takes this raw, validated data and maps it into a simple, technology-agnostic register user request data transfer object, DTO. This DTO is defined in the interface adapters layer or the use cases layer. It contains only the specific pieces of information that the core business logic needs to perform the registration, completely devoid of any HTTP or UI-specific baggage. At this stage, the web controller does not contain the business logic for user registration itself. Its responsibility is to prepare the data and then hand it off to the next layer. Step 3. Invoking the use case, primary adapter interface adapters layer to use case layer. Once the register user request DTO is prepared, the web controller, primary adapter, then invokes the core logic of your application. It does this by calling a method on an interface defined in the use cases layer. The web controller has a reference to an iRegister user use case, an interface defined in the use cases layer. It calls the execute method on this interface, passing the register user request DTO. The dependency rule is maintained because the web controller outer layer knows about and depends on the iRegister user use case interface, inner layer. Step 4. Executing business logic, inner layer, use cases. Now, the control enters the register user use case, the concrete implementation of iRegister user use case in the use cases layer. This is the focal point where the application's specific business rules are orchestrated. The register user use case performs the following steps. Business validation. It now applies the more sophisticated business rules. Uniqueness check. Does a user with this username or email already exist? To do this, it calls a method on an iUser repository, an output port interface defined in the interface adapters or use cases layer. For example, user repository find by username, request.username. Password policy. Does the password meet complexity requirements, minimum length, special characters, etc.? Any other core business rule specific to user registration. If validations fail, the use case constructs an error response. Password hashing. It securely hashes the user's password. This is a core security concern. Entity creation. It creates a new user entity from the entities layer. This entity contains the pure business data and rules related to a user, e.g., user set password, hashed password, which might internally enforce rules about password updates. Persistence via output port. To save the user entity, the use case once again uses an abstraction. It calls user repository save, user. Remember, user repository is just an instance of the iUser repository interface. The register user use case has no idea how the user will actually be saved. It only knows that it needs to be saved and calls the appropriate interface method. Side effect / notification via output port. The registration process also requires sending a welcome email. The register user use case calls email service send welcome email, user get email, user get username, on an iEmail service, another output port interface. Again, the use case doesn't know which email service provider will be used, only that an email needs to be sent. Construct response. Finally, the use case constructs a register user response DTO, which contains the relevant output, e.g., the newly registered user's ID, a success flag, or a list of validation errors. Throughout this entire process, the register user use case relies entirely on its injected dependencies, like iUser repository and iEmail service, which are abstract interfaces. It has no direct knowledge of databases, SMTP servers, or HTTP. Step 5. interaction with external systems, outermost layer, frameworks and drivers. At this point, the calls to user repository save, user, and email service send welcome email. Within the register user use case are handled by their concrete implementations, which reside in the outer frameworks and drivers layer. Database adapter, SQL user repository, secondary adapter. The instance of iUser repository injected into the use case is a concrete SQL user repository, or Mongo user repository, Elastic user repository, etc., depending on your chosen database. This adapter implements the iUser repository interface. When save, user is called, this adapter takes the user entity data, which is a pure business object, translates it into a format suitable for the specific database, e.g., maps it to an ORM entity, constructs a SQL insert statement, or prepares a JSON document for a NoSQL DB. Executes the actual database operation, e.g., connecting to a MySQL server and running insert into users. Returns the result, e.g., success confirmation, or an error if a constraint is violated, back to the use case. Email service adapter, SMTP email service, secondary adapter. Similarly, the concrete instance of iEmail service is an SMTP email service, or SendGrid email service, Mailgun email service, etc. This adapter implements the iEmail service interface. When send welcome email is called, this adapter takes the email data, recipient, subject, body, translates it into the format required by the specific email sending technology, e.g., an SMTP message, an API call to a cloud email provider, performs the actual communication with the external email system, returns confirmation or error back to the use case. It's the duty of these adapters in the outer layer to bridge the gap between the clean, abstract world of the use case and the specific, concrete world of external technologies. Step 6. Returning the result to the client interface adapters to outermost layer. Once the register user use case completes, either successfully or with errors, it returns the register user response DTO to the original web controller, primary adapter, that invoked it. The web controller then receives response DTO. It gets the register user response DTO from the use case. Adapts for presentation. It translates this DTO into a suitable format for the user interface. This might involve setting an appropriate HTTP status code, e.g., 201 created for success, 409 conflict if the email was already registered, 400 bad request for validation errors. Constructing a JSON response body, e.g., userid, ABC, status, success, or errors, username already taken. Perhaps dispatching an event if using a publish-subscribe pattern for UI updates. Sends HTTP response. The web controller, working with the web framework, finally sends the complete HTTP response back to the user's browser or mobile app. This complete lifecycle demonstrates the flow. Notice how the core logic, register user use case and user entity, remains untouched by the specifics of HTTP, SQL, or SMTP. It interacts with these details only through clearly defined, abstract interfaces, the output ports, the concrete implementations of these interfaces, the adapters, and the frameworks that host them live in the outermost layers, ensuring they are interchangeable without affecting the core. This is precisely how clean architecture delivers on its promise of independence, testability, and maintainability. Chapter 9, The Untouchable Core, Testing in Clean Architecture. One of the most compelling arguments for adopting clean architecture, and indeed one of its most immediate and tangible benefits, is the significant improvement in a system's testability. When the core business logic is truly independent of external concerns, testing becomes faster, more focused, more reliable, and less brittle. This chapter explores how clean architecture facilitates superior testing strategies. Why testing is easier. The inherent design of clean architecture directly addresses many of the challenges commonly faced when testing software. Isolation, the most significant advantage. Your core business logic, the entities and use cases, can be tested completely in isolation. They have no direct dependencies on databases, web servers, file systems, or external APIs. This means you can test the critical, what-if scenarios of your business rules without needing to spin up an entire application environment. Speed. Because your core tests run in isolation, without involving slow I/O operations, like disk writes or network calls to a database or external service, they execute incredibly fast. You can run hundreds or thousands of unit tests in mere seconds, providing rapid feedback to developers. Reliability. Tests are less prone to breaking due to environmental factors. Is the database connection down? Is the external API rate limiting you? In a clean architecture, your core business logic tests don't care. They only test the logic itself, making them highly reliable. Focus. Tests can be narrowly scoped to verify specific behaviors and outcomes of your business rules. When a test fails, you know precisely which business rule or use case is misbehaving, significantly speeding up debugging and defect resolution. In a traditional, tightly coupled system, testing a piece of business logic might implicitly require a database connection, a web server, and perhaps even a simulated user interface. This makes tests slow, complex to set up, and prone to external flakiness. Clean architecture liberates your testing efforts. Types of tests in clean architecture. Clean architecture naturally encourages a thoughtful and layered testing strategy, often visualized as the test pyramid. Unit tests, the foundation. These form the vast majority and the base of your test pyramid. Unit tests focus on verifying the smallest testable parts of your application in complete isolation. In clean architecture, your primary candidates for unit testing are entities, testing the internal business rules and behavior of your core domain objects, e.g., order.calculatePrice, user change password. Use cases, testing the orchestration of business rules, the sequence of operations, and how they interact with entities and external dependencies, which are mocked. Unit tests are extremely fast. They don't touch external resources. When testing use cases, any dependencies on external services, like databases or email services, are replaced with test doubles, mocks, or stubs. This allows you to simulate specific scenarios, e.g., what happens if saving to the database fails, without actually interacting with a real database. Integration tests, the middle layer. These tests verify the interaction between different components or layers. In clean architecture, integration tests primarily focus on the interface adapters to ensure that they correctly interact with the actual external systems, frameworks, and drivers. Example, testing if your SQL user repository correctly saves data to a real or in-memory database. This might involve setting up a test database, performing an operation, and then querying the database directly to confirm the data was persisted correctly. Example, testing if your SMTP email service correctly interacts with a local SMTP server or an email service API. Integration tests are slower than unit tests because they involve I/O, but they are crucial for ensuring that the plugs fit the sockets and that the data mappings between layers work as expected. They give you confidence that your adapters are correctly translating between your clean core and the noisy outside world. End-to-end tests, the apex. These tests simulate a full user journey through the entire system, from the user interface down to the database and back again. They confirm that all layers are properly integrated and that the application functions correctly from a user's perspective. Example, using a UI automation tool like Selenium or Playwright to navigate to a registration page, fill out the form, click Submit, and verify that the user is logged in and an entry appears in the database. End-to-end tests are the slowest and most fragile type of test because they involve every part of the system and many external dependencies. Therefore, they should be fewer in number compared to unit and integration tests. In clean architecture, because your core is so well tested by unit tests, your end-to-end tests primarily focus on verifying the complete data flow and integration across all the actual adapters. The power of mocking and stubbing. Test doubles are indispensable tools in clean architecture's testing strategy, particularly for unit testing the use cases. Mocks. These are sophisticated test doubles that record method calls. You can then assert that specific methods were called, with specific arguments, a specific number of times. When testing a register user use case, you might mock iUser repository to verify that save, was called with the correct user entity after successful validation. Stubs, these are simpler test doubles that provide predefined answers to method calls. When testing a use case that relies on iUser repository find by username, you might stub this method to return null, user not found, or a pre-existing user object, user found, to simulate different scenarios. By using mocks and stubs, you can precisely control the behavior of the external dependencies of your use cases. This isolates the use case's logic, making tests deterministic, repeatable, and fast. You're testing the core business rule, not the underlying database or network connection. Case study, testing the register user use case. Let's revisit our register user use case from Chapter 8. How would we test it using clean architecture's principles? Traditional, coupled approach challenge. If register user use case directly instantiated a SQL connection or a Kafka producer, testing it would be a nightmare. Each test run would require a live database and a Kafka broker. Tests would be slow, prone to network errors, and hard to debug. You'd be testing not just the registration logic, but implicitly also your database connection and Kafka configuration. Clean architecture solution. The use case's dependencies are interfaces. The register user use case explicitly depends on iUser repository and iEmail service interfaces, output ports. It never knows about SQL user repository or SMTP email service directly. Unit testing the use case. To test the register user use case, we can create mock implementations of iUser repository and iEmail service. Scenario 1. Successful registration. We provide a mock iUser repository that, when find by username, is called, returns null, indicating the username is available. When save is called, it does nothing or records that it was called successfully. We provide a mock iEmail service that records if send welcome email was called. We then call register user use case execute valid registration request. Our assertions check that the use case returned a success response. That user repository find by username was called once. That user repository save was called once with the correctly formatted user entity. That email service send welcome email was called once with the correct email address and username. Scenario 2. Username already exists. We provide a mock iUser repository that, when find by username, is called with a specific username, returns a pre-existing user object, simulating a conflict. We call register user use case execute registration request with existing username. Our assertions check that the use case returned an error response, e.g., username already taken. That user repository save was not called. That email service send welcome email was not called. This approach allows us to test all the business logic within the register user use case thoroughly and rapidly without touching a database or sending a single email. The tests are purely focused on the business rules. The test, pyramid, and clean architecture. Clean architecture naturally encourages the traditional test pyramid. By isolating your business logic, you get a solid, wide base of fast, reliable unit tests. Your integration tests focus only on the boundaries, the adapters, making them more efficient. Your end-to-end tests provide high-level confidence that all pieces work together in the production environment, but are fewer in number. This results in an efficient, reliable, and confidence-inspiring testing suite that supports agile development. Building an untouchable core is not just about architectural elegance. It's about delivering tangible benefits in terms of software quality, development speed, and maintainability. A well-designed clean architecture is, almost by definition, a well-tested architecture. Chapter 10, Beyond the Diagram. Practical Considerations and Tools. The clean architecture diagram, with its elegant concentric circles, provides a powerful mental model. However, real-world software projects are built with specific programming languages, frameworks, and tools. This chapter bridges the gap between the theoretical model and the practical application, addressing how to leverage common technologies effectively within the clean architecture paradigm. Framework agnosticism in practice. A central tenet of clean architecture is framework independence. While we strive for this, it doesn't mean you shouldn't use frameworks. It means you use them as the details they are, existing in the outermost layer, and ensuring your core business logic remains oblivious to their specific APIs and conventions. Frameworks are details. Recognize that popular web frameworks, like Spring Boot, ASP.NET Core, Node.js Express, Django, Ruby on Rails, are excellent tools for managing the HTTP request response cycle, routing, and providing utility features. They act as the initial orchestrators of incoming requests, dispatching them to the correct primary adapters, which then call your use cases. For example, in a Java Spring Boot application, your user controller might be annotated with @REST controller and @POST mapping /users. This is framework specific. But inside that controller, the dependency to iRegister user use case, your abstract interface, and the call to register user use case execute is framework agnostic. The framework serves as the glue, not the foundation of your business logic. Configuration and dependency injection. Modern frameworks often provide sophisticated dependency injection, DI containers, or inversion of control, IOC, mechanisms. These are extremely useful in clean architecture. They allow you to define your interfaces, e.g., iUser repository, iEmail service, iRegister user use case. Register their concrete implementations, e.g., SQL user repository, SMTP email sender, register user use case, at application startup. Automatically inject these concrete implementations wherever their corresponding interfaces are declared as dependencies. This means your register user use case simply declares its need for an iUser repository, and the DI container provides the SQL user repository or Mongo user repository, chosen and configured in your outer layers. This wires up the system beautifully without any layer violating the dependency rule. Avoiding framework lock-in. The goal isn't to never use framework features, but to isolate their usage. If a framework provides a convenient utility that doesn't touch core business rules, e.g., a logging utility, a date formatter, it's fine to use it. However, if a framework feature would force your use cases or entities to become dependent on it, then you should consider creating an adapter so that your core remains clean. Databases and persistence. The database is arguably the most common detail that often leaks into core business logic in poorly architected systems. Clean architecture puts it firmly in its place. Database as a detail. Reemphasize that your database is merely a storage mechanism. Your use cases and entities define what data is needed and what rules apply to it, not how it's stored or retrieved. Mapping, the database adapter, is key here. It's responsible for translating between your clean entity objects, which are pure business concepts, and the database-specific models, e.g., an ORM entity or a row in a SQL table, a document in a NoSQL database. When an order entity is passed to a SQL order repository, your adapter, the adapter takes the order's properties and maps them to the columns of the orders table. When data is retrieved, the adapter maps the database rows back into clean order entities. This mapping logic belongs in the interface adapters layer, specifically within the concrete repository implementations. Multiple databases providers. The inherent flexibility means you could use a SQL database for one set of data, a NoSQL database for another, and even a cloud storage service for blobs, all within the same application, by simply providing different adapters for different output ports. User interfaces, web, mobile, desktop. The UI is the most visible outer shell of your application. UI as an adapter. The entire UI layer, web components, mobile activities, desktop forms, acts as a specialized primary adapter. It gathers user input, makes sense of it, marshals it into DTOs, and sends it to the use cases. Conversely, it receives DTOs back from use cases and presents them to the user. Separation of presentation logic. It's vital to keep UI-specific logic, e.g., displaying validation messages next to form fields, handling button animations, managing local UI state, screen transitions, separate from your core application logic. This presentation logic resides firmly in the UI outermost layer, or perhaps in thin, presenter, or viewModel components within the interface adapters layer that are purely concerned with preparing data for display. Reusability. This structured approach enables significant reuse. The same register user use case can be consumed by a web interface, a mobile application, or even a batch import script, simply by implementing different primary adapters for each client. Asynchronous operations, events, and messaging. Modern applications rarely operate in a purely synchronous, request-response manner. Clean architecture can elegantly integrate asynchronous patterns, integrating a sync. When a use case needs to perform an operation that is inherently asynchronous, e.g., sending an email that doesn't block the main thread or publishing an event, it still does so through an output port interface. For instance, iEmail service send email async would be an interface method. The use case calls it and continues. The concrete adapter, e.g., a sync SMTP email sender, would then handle the actual asynchronous invocation using message queues, separate threads, or non-blocking I/O provided by its framework. Event publishers subscribers. If your use case needs to publish an event, e.g., user-registered event, it does so through an iEvent publisher interface, an output port. The concrete Kafka event publisher or RabbitMQ event publisher, adapters in the outer layer, would then handle the technical details of sending the event to the messaging bus. Conversely, event consumers are like primary adapters. They listen for specific events from the message bus and then translate these events into calls to appropriate use cases. Queues as external agencies. Message queues or event streams should be treated as external systems interacted with via adapters, just like databases or web services. The use case defines the contract, the message format, and the interface to send/receive it, and the outer layer implements the specific technology. Microservices and clean architecture. Clean architecture principles are highly complementary to microservice architecture. Internal consistency. Each individual microservice, no matter how small, can and should benefit from adopting clean architecture internally. This ensures that even within a distributed landscape, each service maintains its own clean core business logic, testability, and maintainability. A microservice is essentially a deployment boundary, but good internal architecture for that service is still crucial. Clear boundaries. Just as clean architecture establishes clear boundaries between layers within a single application, it reinforces the broader concept of clear API boundaries and contracts between independent microservices. Each microservice essentially treats other services as external details that it interacts with via well-defined adapters, APIs. A microservice typically exposes its use cases via a web API, which is a form of primary adapter. Beyond monoliths, the concepts scale. Whether you're building a traditional monolithic application composed of distinct modules or a complex distributed system of microservices, the philosophy holds. Protect your core business logic, make it independent of infrastructure, and adapt to change by swapping out external details, not by rewriting your fundamental value propositions. This principled approach provides a robust foundation for building maintainable and adaptable software, no matter the scale. Understanding these practical applications ensures that clean architecture remains a pragmatic guide, not just an abstract ideal. It shows how the diagram transcends mere theory and becomes a powerful compass for navigating the complexities inherent in building resilient software systems today. Chapter 11. Common missteps and debunking myths. Like any powerful architectural pattern or methodology, clean architecture, while offering immense benefits, is often subject to misunderstandings, common missteps in its application, and outright myths. This chapter aims to clarify these points, providing a more balanced and pragmatic view and helping you navigate the pitfalls that can arise from misinterpreting its principles. Myth 1. It's overengineering for small projects. This is perhaps the most common criticism leveled against clean architecture. The argument suggests that the overhead of setting up interfaces, DTOs, and distinct layers is too much for a small startup or a simple application that just needs to get built quickly. Rebuttal. Investment, not just cost. Clean architecture is an investment. While there's undeniably an initial setup cost in terms of upfront design and code structure, this cost is repaid many times over in the form of reduced long-term maintenance, faster feature delivery, and higher stability. Small projects often grow into large ones unexpectedly. An architecture-agnostic, small project quickly becomes a tangled, rigid, and fragile, large project. Small is relative. What defines a small project? A microservice might seem small, but if it's critical to business operations and expected to evolve for years, the investment in clean architecture is incredibly valuable. Even a simple CRUD application, if it touches complex business rules, e.g., specific pricing calculations, complex user roles, will benefit from isolating those rules. Pragmatism. For truly short-lived, throwaway scripts or simple prototypes that you know will never evolve, applying every single clean architecture guideline might indeed be overkill. The point, however, is to understand the principles and apply them pragmatically where the benefit outweighs the overhead. Even in simple projects, thinking about what is my core business logic and how can I separate it from UI and database is always beneficial. Myth 2, it's too much boilerplate code. Critics often point to the proliferation of interfaces, DTOs, request DTOs, response DTOs, mapping between DTOs and entities, and several layers of abstraction as unnecessary boilerplate. Rebuttal. Valuable structure, not just ceremony. What seems like boilerplate is actually valuable structure and intentional decoupling. Each DTO and interface serves a specific purpose: to define clear boundaries, allow independent evolution, and facilitate testability. This ceremony captures design decisions and ensures adherence to the dependency rule, preventing technical debt from accumulating. Automation helps. Many modern programming languages and IDEs offer tools or libraries to reduce boilerplate. Code generation tools, build time transformers, or annotation processors can automate some of the repetitive mapping or interface creation. Long-term gain. The overhead of writing DTOs and interfaces up front is negligible compared to the cost of untangling tightly coupled code when business requirements change drastically years later. It's paying a small tax now to avoid a massive debt later. Myth 3, it dictates my technology choices. Some believe clean architecture forces them into specific programming languages, frameworks, or database technologies. Rebuttal, technology independence. This is the exact opposite of what clean architecture advocates. Its core promise is independence from technology details. It provides a framework for how to use any framework, database, or UI technology, not which ones. You can use clean architecture with Java, C#, Python, JavaScript, Go, etc., and with any web framework, any database, any cloud provider. Freedom, not restriction. By isolating technology to the outermost layer, clean architecture grants you the freedom to swap out these technologies later if better alternatives emerge or business needs change, without affecting your core business logic. Myth 4, my UI database is my architecture. This is a common misconception, especially among developers who have primarily worked on tightly coupled applications. They might define their application by its chosen web framework, e.g., it's a Spring Boot app, or its database, e.g., it's a microservices app with MongoDB. Rebuttal, external details. As we've emphasized, the UI, database, and frameworks are external details in clean architecture. While they are crucial for the application to function, they are not the essence of its architecture. Business rules are core. The true architecture lies in the organization and relationships of your core business, rules, entities, and use cases, and how they remain independent and protected. Your business logic could theoretically function without a UI or database, simply by being driven by automated tests or a command line interface. Myth 5, it's just a fancy name for layers. Layered architectures have existed for a long time, e.g., model view controller, N-tier architecture. Some might dismiss clean architecture as just another variation. Rebuttal, the critical differentiator. The dependency rule. While clean architecture uses layers, its unique power comes from the strict enforcement of the dependency rule. Dependencies must always point inwards. Many traditional layered architectures do not enforce this strictly, leading to leaky layers, where inner layers inadvertently become coupled to outer layers, e.g., a business logic layer knowing about specific database access details. This seemingly small difference makes a profound impact on testability, maintainability, and adaptability. The pitfall of leaky abstractions. Even when trying to implement clean architecture, a common pitfall is the accidental creation of leaky abstractions. This happens when an implementation detail from an outer layer, e.g., a specific database-dependent error code, a framework-specific exception, surfaces into an inner layer or across a boundary where it shouldn't. Example: if a user registration failed exception thrown by your SQL user repository outer layer has details specific to SQL, e.g., constraint violation on userid column, and your register user use case inner layer catches this specific SQL exception, then your use case has become coupled to your database technology. Instead, the SQL user repository should catch that SQL exception and translate it into a generic duplicate user exception or persistence failed exception that the use case can understand without knowing the underlying database. Protection: DTOs help with this as they act as explicit contracts for data transfer. Being vigilant about what information passes across boundaries is crucial. Over-abstraction, too many layers interfaces. While abstraction is key, it's also possible to go too far. Creating unnecessary interfaces or layers where none are truly needed can lead to increased complexity. More files, more navigation, and less direct code paths can actually make the system harder to understand, not easier. Boilerplate without benefit. If a component truly has no alternative implementations now or in the foreseeable future, an interface might be premature abstraction. Reduced development speed, initially. Spending excessive time on hypothetical abstractions that never materialize can hinder progress. Finding the right balance. The goal is maximum decoupling with minimum effort. Start with the core business rules and build out from there. Introducing interfaces and adapters where they truly serve the purpose of protecting a stable internal policy from a volatile external detail. Use your judgment based on whether a component is truly likely to have interchangeable implementations or is a stable piece unlikely to change. Finding the right balance. Pragmatism over dogmatism. Clean architecture provides a powerful compass, but it's not a rigid set of dogmatic commandments to follow blindly in every scenario. Understanding the why behind its rules allows for informed deviations when necessary. Start with the core. Always identify your true business logic first. What is the stable core that defines your unique value? Protect that above all else. Be mindful of overhead. While valuable, acknowledge the overhead. It might be acceptable to take a small leak for a truly tiny internal tool that will never connect to anything and will be rewritten next month. But understand the trade-off. Iterate and refine. Architecture is not a one-time activity. As your system evolves, you might refactor parts of it to better align with clean architecture, or you might realize a previously simple component now needs more robust architectural separation. Clean architecture challenges traditional ways of thinking about software structure, often requiring a paradigm shift. By dissecting these common misunderstandings and potential missteps, we can approach its implementation with greater clarity and a more pragmatic mindset, ultimately building more resilient and maintainable systems. In our final chapter, we will discuss practical strategies for adopting clean architecture in your own projects. Chapter 12. Bringing it home. Adopting clean architecture in your projects. We've journeyed through the philosophy, structure, and practicalities of clean architecture, demonstrating its profound impact on testability, maintainability, and adaptability. Now, for the most crucial question. How do you take these concepts from the pages of this book and apply them to your own software development projects? Whether you're embarking on a brand new application or wrestling with an existing code base, strategic adoption is key. Starting small, greenfield projects. For new projects, clean architecture offers an ideal foundation. You have the luxury of designing with its principles from the ground up, minimizing the burden of refactoring legacy code. Begin with the core. Don't start with the UI or the database. Instead, begin by identifying and defining your core entities, the enterprise business rules, and your top-level use cases, the application-specific business rules. These are the most stable parts of your system. Focus on pure business logic, defining the inputs and outputs of your use cases as simple, technology-agnostic DTOs. Implement the core first, test-driven. Write unit tests for your entities and use cases as you develop them. Since they have no external dependencies, These tests will be fast and reliable, providing immediate feedback and ensuring your core logic is sound from day one. You can even use simple in-memory storage for initial testing, deferring the database choice. Build outwards with adapters. Once your core is robust, gradually build the outer layers, define output ports. As your use cases need to interact with external systems, like a database or an email service, define the abstract interfaces, output ports, they need, e.g., iUser repository, iEmail service. Implement adapters. Then, in the interface adapters layer, create concrete implementations of these interfaces, e.g., SQL user repository, SMTP email service. These will then use the actual frameworks or drivers in the outermost layer. Construct primary adapters, UI API. Finally, build your user interface or API controllers, which will serve as the primary adapters, orchestrating user input into calls to your use cases and presenting their results. Embrace an iterative approach. Don't try to architect every single detail upfront. Clean architecture lends itself well to iterative development. Define the most crucial use cases and build those out. As new features are required, integrate them into the existing architectural pattern. This organic growth ensures that your architecture evolves with your understanding of the problem domain. Incremental adoption, brownfield projects/existing codebases. Refactoring an existing, tightly coupled codebase to clean architecture can be a daunting task. It's often impractical, if not impossible, to achieve it in one giant overhaul. The key is to adopt an incremental strategy, the strangler fig pattern. This well-known pattern, coined by Martin Fowler, is an excellent metaphor. Imagine a new, strong strangler fig tree growing around an old, decaying tree, eventually consuming it entirely. In software, this means gradually replacing tightly coupled parts of a legacy system with new, clean components built using clean architecture principles. Focus on a new feature. Choose one new, significant feature or a small, isolated module that is critical for the business. Implement only this new feature using clean architecture. This allows your team to learn the patterns, validate the benefits, and demonstrate success without overwhelming the entire codebase. Other teams often see the benefits, easier testing, faster development, and start asking for the same. Identify and extract core logic. Look for pure business rules embedded in your legacy code, e.g., in service classes, utility methods, or even UI code. Gradually extract this logic into new entities and use cases, divorcing them from their database or UI dependencies. Define interfaces for existing dependencies, where your extracted core logic needs to interact with functionality still residing in the legacy system, e.g., an old database access layer, a proprietary logging system. Define an interface, an output port, for that dependency. Create adapters for legacy systems. Implement an adapter that conforms to this new interface, but delegates to the existing legacy component. This allows your new clean architecture components to interact with the legacy system without being coupled to its internal structure. Over time, as the legacy system is phased out, you can replace these legacy adapters with new, cleaner implementations. Refactor to use cases. Gradually reshape application logic into independent use cases. This might involve identifying existing service methods and refactoring them to clearly defined use case inputs, outputs, and orchestrators of entities and output ports. This incremental approach reduces risk, provides continuous value, and allows your team to gain experience and confidence over time. Team buy-in and education. Implementing a new architectural style is not just a technical challenge, it's also a cultural one. Effective adoption requires strong communication and education. Communicate the why, clearly explain why you are adopting clean architecture. Emphasize the benefits for the team. Easier testing, fewer bugs, faster development of new features, reduced developer frustration, and improved job satisfaction. Frame it as an investment in sustainable development and team well-being. Workshops and training. Conduct regular internal workshops or study groups to familiarize the team with the concepts, principles, and specific implementation patterns. Use concrete examples relevant to your domain. Start with shared vocabulary. Ensure everyone understands terms like entities, Use cases, ports, and adapters. Architectural champions. Designate one or more team members as architectural champions. Their role is to guide the team, answer questions, provide code reviews from an architectural perspective, and ensure consistency in the implementation of the patterns. This ensures knowledge transfer and maintains architectural integrity. Lead by example. The architectural champions, or senior developers, should start by implementing the first few use cases and their surrounding adapters, providing concrete examples for others to follow. Measuring success. How will you know the investment in clean architecture is paying off? Look for these indicators. Reduced bugs, especially within your core business logic, indicating improved quality and testability. Faster feature delivery. Once the initial investment is realized, you should observe a quicker turnaround time for new features due to reduced architectural friction and improved agility. Lower technical debt. Less need for costly, large-scale refactoring and an overall healthier codebase. Happier developers. A more pleasant codebase to work on, reducing friction, frustration, and ultimately, developer burnout. Improved test coverage and reliability. Your test suites should be faster, more stable, and provide higher confidence in changes. Ease of change, the true measure of good architecture. Can you easily swap out a database, change a UI, or introduce a new external service with minimal impact on your core logic? Conclusion: bringing it home. Clean architecture is not a silver bullet that solves all software development problems instantly. It requires discipline, initial investment, and a cultural shift. But it provides a powerful, enduring framework for building software that is resilient, adaptable, and long-lasting. It represents a fundamental shift in mindset, putting your core business value at the absolute center of your efforts and consciously treating often complex infrastructure, databases, frameworks, UIs, external services as interchangeable details. It liberates your business logic from the constant churn of technology trends, ensuring that your application can deliver value for years, even decades. In a rapidly evolving technological landscape, the ability to protect and maintain your core business rules is paramount. Clean architecture empowers you to do just that, allowing you to build not just software, but truly enduring code. By embracing its principles, you are not just writing programs. You are laying the foundations for systems that can evolve, adapt, and stand the test of time, creating a lasting legacy in the digital world. This principled approach is a vital skill for any modern software professional committed to building robust, high-quality applications.